Right. Hello, everyone. My name is Stephen Hoover, and I'm here from Civis Analytics. Civis Analytics offers a cloud-based data science platform that helps data scientists to scale their data, accelerate their workflows, schedule, and share. And I'm going to be talking about, recently I led an effort to replace the machine learning backend in that platform with the new machine learning backend based around scikit-learn. And this presentation is about the how and the why of that. Since you're here at PyData, you probably care about machine learning already. But organizations everywhere are finding that it's a good idea to use the data that they have to make better decisions. And sometimes you can use your laptop for this, but sometimes you can't. Sometimes your data sets are too large. Sometimes you don't want your data and your work to be trapped on your own machine. And sometimes you just have better things to do with your laptop than to leave it sitting open all night, fitting a random forest. So you can get around this by going to a cloud-based infrastructure. In the cloud, you have access to larger databases, more resources, more and more persistent compute, and a shared environment so that you can collaborate with other people. The Civis Data Science Platform started as a way for us to accelerate our own consulting work. The original machine learning capabilities were fit to what we needed to do at the time. We were doing a lot of work in SQL, so it needed to interface well with SQL database, and we were doing a lot of feature engineering there, and it ended up being that we were doing mostly linear models. As we grew, we developed more sophisticated workflows, and especially as we opened up the platform to other clients, we found that we needed something more powerful, more sophisticated, and more flexible. And that's why we decided to replace the machine learning capabilities with new ones based entirely around scikit-learn, or rather the scikit-learn API more specifically. Why scikit-learn? So scikit-learn is a standard in Python machine learning. Everybody knows it. We don't want to force people to learn new tools. And because it's a standard, there's a lot of tooling built up around it already. It's flexible and extensible. If there's something that's not available for scikit-learn, then you can make it yourself. And in fact, we've made our own extensions in several places. I'm sure many of you have as well. The reason you can do that is because there's a standard interface. There's a way that all of the code objects in scikit-learn interact with each other. And what I'm talking about there is the API. Scikit-learn has a very well-defined, rigid API. Rigid in a good way, I'd say. Because it's so well-defined, you can fit pieces together. The core of that is fit. You want to learn from your data, you call fit. You want to use those learnings on new data, you can call predict or transform, depending on what it is. And your model is not just one piece. Your model is not just your classifier. Your model includes all of your feature extraction steps, all of your missing value imputations, all of that. And scikit-learn provides an abstraction so that you can wrap that all together into a single object. There's multiple higher level abstractions. One of the more powerful ones is this pipeline. Pipeline lets you wrap up several steps so that it all looks like a single model. You can use it as one piece, you can store it and take it back out as one piece. Fit, predict. By doing this, by using these abstractions, you can create your own tools. For example, at Civis, we've created an open source library called Muffin, which wraps TensorFlow. TensorFlow itself isn't scikit-learn compatible, but we've put that inside wrappers which mean that by making our machine learning backend around the scikit-learn API, we get deep learning for free. You know, it's part of the scikit-learn API now. And that's the software. What kind of hardware are we working with? We don't want to do a lot of extra re-engineering of our infrastructure, so we want to work with what we have available already. The Civis Data Science Platform is going to handle all of the user interactions for us. There's an API, there's a graphical user interface, it's handling security, it's handling AWS resource management. The pieces of AWS infrastructure that we have to work with for this are three main pieces. One is Redshift. Redshift is a massively parallel processing database. This is what we use as our primary data store. We have S3 available for staging data, and we use EC2 for arbitrary computation. In fact, we can launch more EC2 instances on demand. We use Docker containers to make sure that the environment that we have there is reproducible. You don't just say, run this job, you say, run this job in this Docker container, and you know it's going to run for sure because you know what environment it's running in. That's been really helpful for us. There's two kinds of scaling that I want to address in this talk today. One kind of scaling is this horizontal scaling. This may seem trivial, but I think it's a really important point. If you want to train your model and check over several different hyperparameters, maybe you have 15, 20, 50 different hyperparameter combinations you want to check, you want to do that all at once, not in serial. Or often we run into situations where we want to simultaneously train models on a dozen different dependent variables. Again, that's something that you want to do in parallel, not in serial. The other kind of data scaling that I want to discuss is data. And that's what we use Redshift and S3 for. Redshift is a petabyte scale database. We don't generally use petabyte scale individual tables, but the tables that we use are still big enough that they're not going to all fit inside a single EC2's memory at once. Requirements: we have to be able to use data from Redshift, as I said. It's a primary data store. In particular, we want to be able to use large-scale data from Redshift. When I say big here, what I mean is data that doesn't necessarily fit into RAM on a single machine. To make things a little bit easier, for this first iteration of our modeling tool, we're only using large data for predictions. Most of our use cases involve data that fits in memory for training, but data that doesn't fit in memory for predictions. So that's what I'm going to focus on. Why can't you just go ahead and call fit on your scikit-learn object? So you've got your pipeline, why not just fit? X and Y, they have to be NumPy arrays, but we don't have NumPy arrays, we have a large table in Redshift. So unfortunately, we can't just put our scikit-learn code into Redshift. Redshift doesn't work that way. We have to pull the data out. Redshift's favorite way of unloading data, by far the fastest and the easiest, is to dump everything into a CSV. So we dump it into a CSV, move that into S3. From S3, we copy it into EC2. You can use pandas to read that in. Then going through a CSV, you can lose type information, which is not so great. A particular corner case, which is not so corner because we run into it all the time, is that you have a column which is a string, but it looks like an integer. Maybe 1, 2, 3, except as strings, which is all fine and good until row number 22,338 has A123 instead of 123. And if you do your type inference from the first few rows, you'll get an error. Not fun. So you can read type information from Redshift. We don't use the type information directly, we cast it, casting all numerical values to float 32s for a couple of reasons. One is that you don't need 64-bit precision for this kind of work, and you save a lot of RAM by cutting that in half. The other is that you need homogeneous data types for your NumPy arrays anyway. And finally, pandas treats missing values as NumPy NANs. NANs are float types, and that means that if your integer column has or might ever have a missing value in it, you need to be treating it as a float value. Right, and finally, we have to know which of those columns are features, which of those columns are targets. For that, you have to ask the user to point out which columns are which, and pull those out and arrange them into arrays. Next problem is that some of these features might be strings. Scikit-learn doesn't deal with strings natively, so you have to convert your strings into numeric types. Pandas has a getDummies function, which is nice when you're doing data exploration, but there's a couple problems with that. One is that there's no obvious way to use that to reproduce the same one-hot encoding on a future data set. Another problem is that it has excessive RAM use, and so we wrote our own one-hot encoding with repeated applications of a scikit-learn label encoder. That's worked out really well for us. Then what about prediction? So first step for prediction is that you have to get the data into your EC2 instance, same as before. New wrinkle is that you need to make sure that your features are in the same order as they were for training. You have an unlabeled array when you're working in scikit-learn, and if you happen to transpose some columns, then your predictions are no longer going to be relevant or correct. Solve that. You store metadata. You record what order the columns were when you did your training, and you can reproduce that for prediction. Another problem is that we want to be able to upgrade this code every once in a while. We want to be able to make changes, but we also want to make sure that the models you train today, you can make predictions with tomorrow, next week, or next year. And for that, we wrap everything inside a Docker container, and we use semantic versioning. With semantic versioning, that's your 3-point version numbers, 1.2.3. The first number increases whenever you have API breaking changes. For us, there's two kinds of API breaking changes. One is if something the user is inputting changes what it does. That's obviously API breaking. Another important kind of API breaking is if your training job no longer produces, your prediction job no longer works with the outputs of the previous version's training job. That is also an API breaking change that we want to record. We also want users to be aware of new releases, new feature additions. If we change the way that we're doing modeling, for example, maybe it's not an API breaking change, but it might change, at least subtly, the kinds of results that you get out of your pipeline, and we don't want automated workflows to change out from under people, so that's something they have to opt into. And finally, bug fix versions, those don't change any existing functionality. We do produce, for archival purposes, Docker containers with the full major, minor, micro version tags. But in production, we run Docker containers that are tagged with major and minor versions only. And we rewrite those with new versions whenever we have bug fixes. That lets us transparently deploy any fixes into production. Finally, going back to scaling, maybe your data sets are really, really big. Fortunately, prediction is an embarrassingly parallel task. You can take your data and divide it up. You don't care about looking at row number 5 when you're making predictions with row number 20. And Redshift gives you, the fastest way to export data from Redshift actually gives you multiple CSVs. In fact, it gives you CSVs with a maximum size of 6.2 gigabytes. And that is not too large as to be unwieldy. So we take those CSVs and we move them into our Docker containers and run prediction tasks on each of those separately. When you run the training, you serialize your model, take your scikit-learn pipeline after it's been trained, store it and upload it to S3, separately upload a JSON blob of metadata. When you're running predictions, you pull those back down, pull those into the Docker containers, unpack them, and run them on each CSV. And for even better memory use purposes, we don't have to read the entire CSV into memory at once. It's easy to iterate over just chunks of that CSV. So we read in a few thousand rows at a time, make predictions, write the predictions out, read in the next few thousand rows, make predictions, append that, so forth and so on until you've gone through the entire CSV. Some things that you need to remember if you're doing something like this. The first is that bandwidth is not infinite, especially if you're moving large amounts of data around. That takes time. So compression is your friend. Make sure to compress everything. The next problem is that every API call, every network communication that you make takes some amount of time. And you want to minimize that time. You want to minimize the number of network communications that you make. And possibly an even more important reason to minimize the number of network communications that you make is that you're going to have failures. If you're running predictions on hundreds of chunks of data at once, then the chance that at least one of those is going to hit a 500 error sometime is going to approach 1. So you want to first minimize the number of times that you have to communicate over the network. Second, you want to make sure that you are wrapping all of those network communications in retries. Right. Now, a little bit about the tooling that we use. Joblib is a library in Python that facilitates parallel processing. I'll give a quick call out to the serialization functionality. If you pickle in Python, pickling is inefficient for storing NumPy arrays. Joblib has a pickling plus functionality. It will pickle objects unless they are NumPy arrays, in which case it uses NumPy save. It's much more efficient. You should use that if you're moving data around. Joblib also provides parallel processing capabilities. Parallel processing with Joblib looks like this. You take the function that you want to parallelize, you wrap it in this delayed decorator, and then you feed an iterator of calls to this delayed function into the parallel class. JobLib provides an easy way for you to swap out the backend that you're using for these predictions. Here, multiprocessing is the default JobLib backend, and here I'm specifying that explicitly. Multiprocessing means using Python's built-in multiprocessing library to parallelize over different Python processes. JobLib also has a threading backend if you don't care about the GIL. But importantly, JobLib lets you write your own custom backends. We've done this for the Civis platform, and you can use this syntax, which is pretty easy, to parallelize your code in the cloud. You run this register parallel backend function from JobLib, and this tells JobLib to run a new, to use the Civis backend, you call this function here. I tell it to use Civis backend, and now this square root function is parallelized in the cloud, which is nice and all, but maybe a little boring. More interestingly, scikit-learn internally uses JobLib to parallelize its code. And this is almost entirely pure scikit-learn code. The one bit that I've added is now I'm registering this new parallel backend Civis, and by running inside the with parallel backend Civis context, this grid search is now parallelized on AWS using a different EC2 instance for each node in the hyperparameter search. If you want to make your own custom JobLib backend, the first thing you do is you subclass this parallel backend base abstract class. When you do this, there's two methods you need to override. One is effective number of jobs. That's pretty simple. How many jobs can this run at a time? The other is apply async. Apply async needs to take a function as input, and it needs to return immediately with a delayed result. That result is the other thing that you need to write. Oh, sorry. Optional but highly recommended is this abort everything method. If JobLib runs into an error in one of the subjobs that it's processing, it will stop immediately and print an error message to the screen for the user. It will assume that if one job fails, all of them fail. And if you provide an abort everything method on your back end, then JobLib will call that for you. Maybe this doesn't matter quite so much if you're running in different processes on your own machine, but if you launched 100 jobs in the cloud and one of them fails, you don't want to leave the other 99 running. You'd be nice to shut those down and free up those resources so that you don't wait for them all to finish when you're going to be ignoring the results anyway. So abort everything is a useful thing to do. The result class, your apply async method needs to output one of these results. And it doesn't have to be a subclass of anything. It's duck typed. The thing that it quacks like is a standard library async result object. Slight differences, you need to take a callback function in the init. JobLib uses these callback functions so that it can know when an individual process is finished and when it can add new processes to, when it can start working on new chunks of work. The other thing you need to implement is this git method. Git needs to be blocking. You call git, and it should return the result of the chunk of work that it was assigned. It also needs to call this callback function. Optional, but nice to use, is the transportable exception. If you have an error in your remote job, if you can wrap that in a transportable exception and send it back to JobLib, then JobLib will be able to display the traceback on the screen, give more information to the user about what went wrong. It's difficult enough debugging errors in distributed computing. You want to make this as easy on yourself as possible, so I recommend using the transportable exception. The way we've implemented this, we already had an implementation of the standard library executor module, or executor class, which launched jobs in the Civis platform. And the executors in the concurrent futures module submit returns a future. If you aren't familiar with the future abstraction, that's definitely worth taking a look at. I find that it's a really convenient way to do asynchronous computation. In particular, for this use, the future lets us retry jobs pretty easily. When the remote job is complete, then it will set its state on the future object. If it's successful, all well and good. If it fails, it's going to set an exception. If you can, we intercept attempts to set that exception, and if their user has requested retries, then we automatically retry. And that transparently and immediately retries jobs as soon as they fail. The other thing that we have in to make the joblib backend work is a wrapper function. When we're sending data out to run in the Civis platform, we pack that function up and store it in S3. When we launch the remote job, we're calling this wrapper function. The wrapper function downloads the function from S3, it unpacks it, runs it, and then packages up the results, or the exception, if there was an error, sends it back to S3. And finally, instead of downloading results inside the result object's get method, we use a callback on this future object to download the results as soon as the object is done, as soon as the remote computing is done, and call joblib's callback. And finally, this is all open sourced. If you go to our GitHub repo, Civis Python, that's our API client, you can see the joblib implementation. It's on master branch right now. It'll be in an upcoming release, hopefully in the next week or two. Right, some things to remember when you're doing this. Make sure that the remote environment can execute your code. This is pretty important if your remote environment is a Docker container on EC2. Whatever you pickle, that code needs to be available in your Docker environment. Python doesn't pickle the code underlying the functions, it pickles the reference to the code. So the code itself has to be available in your remote environment installed there. The reason I talked about downloading results as a callback on the future is that result.get will call your results, joblib calls get one at a time in order on all of your chunks of work. If you wait until you call get on your result before you tell joblib that it's done, what we were seeing was that we'd have maybe 20 things to do and assign 10 workers to it. We would use, the first 10 jobs would all complete before we would start the next set of 10 jobs. What you want to do is you want to keep everything working continuously. And that was because even though the jobs had already completed, joblib didn't know until we'd gotten to the place where we actually called get on that chunk of work. So that was solved with the callbacks on the futures. And make sure to retry when you're downloading results. It's really annoying to have a remote job succeed, but then have your entire job crash because you ran into a 500 error when you tried to download the results from S3. That's happened to me more than once. And finally, we make extensive use of the standard library logging module. It's extremely helpful. Joblib uses print statements, so you want to capture those and redirect them into your logger. And using the joblib backend, this is what the implementation of parallel scoring inside the Civis machine learning backend looks like. So like I was showing you before, we register a backend. I think maybe the new thing here is the infer backend factory function. If you're running inside the Civis platform, we're able to introspect our environment so that we can make sure that we're reproducing that on the remote worker. And that solves the problem of making sure that all of the local code is available there. Right. And this then is the modeling interface for Civis modeling tool, CivisML, once everything is finally finished. You can define your scikit-learn, you can define your model as long as it's scikit-learn compatible, register it with the Civis platform, use data that's either local or possibly coming from a Redshift table. And then your train call is non-blocking, it returns a future. You can do whatever other work you want to do in the meantime. Maybe that's launching dozens of other models. And then your predict function, you can run predictions on large-scale data, and it will complete in linear time, because as long as you have enough computational resources available, constant time, as long as you have enough computational resources available. And it's not just objects from the scikit-learn standard library, of course, scikit-learn core library, anything that's scikit-learn compatible. For example, XGBoost. The Python XGBoost library follows the scikit-learn API, so you can use XGBoost models just as easily as you can use anything else. Right, and so that's a little bit about our implementation. Thank you for listening, and happy to take questions.
How do you compare between your platform and the approach using Spark to parallelize the machine learning prediction or training? What's different method?
Okay, the question was how do we compare this to using Spark to do machine learning on large data, right? Yeah, I think Spark's machine learning is great if you have huge data sets to train on. There's very limited algorithms available because a lot of algorithms don't parallelize for training. And what we're doing here is we're trying to take the code that you're used to writing with scikit-learn and let you run that in the cloud.
So what if you also install scikit-learn in individual machines, individual node, and then just use Spark to distribute the data?
Yeah, so what if you install scikit-learn in the individual nodes and use Spark to distribute the data?
Yeah.
Yeah, you should be able to do that for scoring as well. I don't think I don't remember, I haven't explored that myself, but yeah, that should be possible. That's another way to parallelize it instead of using something like this joblib backend.
Will you compare Dask with joblib?
The question is, how do I compare Dask with joblib? I think joblib you can use for parallelizing individual functions. I think you could probably use Dask bag or something like that for this as well. But Dask, as I understand it, is if you want to do, say, split up large matrix computations over many processes or many nodes, then you could use Dask for something like this. I think for this particular task, it would end up being functionally equivalent.
So the training step is non-blocking. It does all this grid search parallelly. But the predict step, you wait for the results. And it still does parallelly predictions on your data set and returns you the combined results?
Yeah, the question is, the train step is non-blocking, which is correct. And then the predict, you have to wait until the train is complete, of course. And then, yeah, the prediction step is non-blocking, and it runs each chunk of your large data is run in parallel. And then those are combined back into a single table at the end.
A follow-up question. So when you have your data set in S3 or something, then you predict you give the S3 location for your data set.
The question was if you can predict from a data set in S3 and just give it the location. Yeah, you can do that.
Does joblib have support or will have support for like a more generalized distributed task execution system like Apache or Flows?
The question is if joblib is going to have support for a more generalized task execution system. I'm not aware of any plans for anything like that, no. Dask might be a better place to see something like that happen, since Dask is building interfaces to distributed computing. Yeah.
Can you talk about it looks like you use Redshift for all your backend storage. Can you talk about the design choice of using Redshift over other cloud products like RDS?
Right. The question is, can I talk about some of the design choices behind using Redshift for our storage instead of other options such as RDS? We found that Redshift has been a really good solution for very large-scale SQL queries. If you're interested in doing joins between large data sets or group bys, then Redshift is a good solution for that. I think RDS is a lot better for single row operations, but the use case that we had originally was more large-scale data and joins and column operations, which Redshift is optimized for.
So in terms of the number of nodes that you want to run this job on, like, do you like, do you specify in the code where, like, how many nodes you want to run, or does the system do it behind the scene transparently, depending on how large the workload is?
The question is how you decide how many nodes this runs on. Yeah, the user has to specify how many jobs that they're going to let the system use. And that's a maximum number. If it can't parallelize over quite that many, it won't use quite that many. But you want to avoid hogging too many resources or using more resources than you expected, I think is one reason for that.
And does the user get to specify the CPU, RAM resources for each node, or is that already predefined?
Does the user get to specify CPU and RAM resources for each node? For training, the user can specify those resources. For prediction, the user doesn't specify those because the prediction resources are pretty well bounded. We're using small amounts of data, so you don't need much RAM.
Have you looked into using direct RPC to read, directly from Redshift and convert that RPC and into directly NumPy data instead of going through the CSV and this? That might be slower if you have a, like 10 gigabit per second network. Have you looked into that option?
So the question is, have we looked into reading directly from Redshift into the containers rather than going through CSVs first? Was that your question?
Or do you do like a benchmark comparison between different choices like CSVs or direct RPC and other interchain format like protocol buffer and see which one is work best with different situations, like when people have a high bandwidth and when people have a high storage, like SSD storage. You play with that option and have different choices.
Okay, yeah, so you're asking if we've explored different options for reading from Redshift.
Yes.
Yeah, and the dumping to CSVs is the fastest, unfortunately. Redshift is not optimized for row-by-row reads. It's, as I was mentioning before, it's optimized for joins on column. It's optimized for column operations. And if you want to pull the entire data set out as a large block, dumping it to CSVs is actually the fastest way that we found to do that.
Okay.
It does sound weird, I admit. Yes?
Some scikit-learn models have support incremental learning, and I wonder if you explored that.
Yeah, that's actually one of the things that's next on our list to implement. The question was if we're planning on implementing the fit partial method, support for fit partial in scikit-learn so that we can train incrementally on potentially larger data sets. Yeah, that's one of the next things on our list to implement.
Is it open source or you can use?
So the code behind CivSML is not open source, mostly because I'm not sure I want to take the time to clean it up and make it look pretty enough. But the interface in our API client is public, and the joblib backend code is all public now too.
Does it only work on AWS?
Yes, it only works on AWS. Yeah, it's all working through the Civis platform, which is based on AWS. If the Civis platform expanded to use other clouds, then this interface would, the interface itself is relatively agnostic to which cloud resources it's using, but the Civis platform is based in AWS.
All right, so I think we are done. Oh, do you have one?
Oh, this is Spark comparison reporting.